cornerstone for this design, of course, is going to be the electromagnetic analysis. So you no longer just need to do the electromagnetic analysis, as I mentioned. You need to be able to do thermal analysis on your design to take into account the coupled nature of the material properties between thermal and electromagnetics. You need to take into account the structural integrity of your design, especially in the electric vehicle domain, when it comes to the structural integrity and meeting the performance requirements for the entire vehicle. Also, the vibroacoustic analysis, because as the internal combustion engine used to mask a lot of the noises generated by the car. However, nowadays, because of you don't have the masking noise, the noises that comes from the electric machines, from the transmission winds, all of these become very significant and dominant. We have to take into account the vibroacoustic, and it's becoming more and more popular as we progress and we're essentially exploring new techniques in the electric vehicle industry. And the last thing, of course, is the cooling of the electric vehicle. So considering those designs is not just important, it's extremely important to have it also tied in with an intelligent design exploration. So you have to tie in all those physics. When you make a change in the design, you have to take account the other physics and making sure that you're considering as many design variations early in the design stage before building your prototypes, to save from building the prototype cost and making sure you're building a competitive design. So with that being said, let's jump into the technical side or the multiphysics designs, where we'll be looking at 3 different types of analysis. A detailed demagnetization analysis, we're looking into 2 domains, the load current demagnetization and the thermal demagnetization. We're also looking at eccentricity analysis for NVH, where we're using the native functionalities in SimCenter magnet to essentially calculate the force, the surface nodal force that you can then map to your structural analysis to get the NVH analysis. Also, we're looking into the cooling and CFD to optimize the cooling technique, because as we're going to see, we're going to use some of the results from the demagnetization analysis to drive the cooling system design and sizing. So to start off with the current demagnetization, due to the increase in load torque from 100 Newton meter to 200 Newton meter at 120 degrees Celsius. This requires the current to be ramped up as seen in the chart, which results in a corresponding increase in torque. Now let's see the state of the magnets before and after the increase in current. At 5 milliseconds, we can see that the magnets are not demagnetized. And at 20 milliseconds, there is a partial demagnetization, which lowers the torque by 4%. So what is happening to our magnets in the partially demagnetized region? To investigate this, we're going to break the BH loop and the currents into stages. So in the first stage, the magnetized model and the non-demag model will recoil at the same characteristics. So if we take the design, ignore the demagnetization and take the demagnetization into account. In stage 1, we see that the demag and non-demag models recoils at the same characteristics. In stage 2, the current is ramped up, as you can see from the graph on the top left corner. The current is increasing. So for the demag model, this is progressive demagnetization as the material is pushed below the knee point and recoils in a new but lower characteristics at every time. And in the final stage, the current settles at the higher current value. Hence, the demag model recoils in a new lower characteristics than in stage 2. And this is important in the analysis of permanent magnet traction motors under all conditions, particularly under acceleration, which requires the motor to be momentarily overloaded. The non-demag model is linear and does not account for field demagnetization, but it is temperature dependent, and it always recoils on the same characteristics as seen from the blue line. And this will result in overestimation of the performance. So now let's see the case of reducing the load. In the case where the torque is reduced from 200 Newton meters to 100 Newton meters at 20 degrees Celsius, at 5 milliseconds, we can see that the magnets are already demagnetized by the high load current. And at 20 milliseconds, the same portions of the magnets are confirmed to be permanently demagnetized. And sim-center magnet can therefore simulate the effects of permanent demagnetization loss, which lowers the motor torque and density. And if the loss is severe, the motor would need to be replaced, since high energy magnets like NEO, for example, cannot be magnetized on the fly. And of course, let's check the magnet characteristics at the same sampling point that we have here at the center of the magnets. When the magnet recoils at the lower characteristics, it's a good indicator that the permanent magnet is demagnetized from the 3 sections. So breaking down the current into 3 sections, we can see now, since we're starting off with the high load current, this automatically pushes the DMAG model to recoil at the same stages for stage 1 and stage 2, and all the stages essentially fall into the same BH loop, which indicates a total or a permanent demagnetization loss. And of course, the second scenario is the thermal demagnetization under low demand. And I will consider an increase in torque from 100 Newton meter to 200 Newton meter, taking into account a temperature rise from 120 degrees Celsius to 150 degrees Celsius. So we're taking both factors into account. Then, and of course, we're increasing the current to take into account the change, and also looking at just the DMAG model. So under the non-DMAG model, which is the blue one, the effect of the temperature is minimal. And it's about 2% overall reduction in the torque. And this is because of the slight difference in the magnet characteristics at the 2 temperatures. Also remember that the non-DMAG model does not account for the field demagnetization, and it always recoils at the same characteristics for a given measure. And that is, it neglects the currents of field demagnetization. Under the DMAG model, the effect of both higher temperature and current is very significant, and it results in a 27% reduction in torque. And this is because a combination of both higher temperature and current that lowers the field required to demagnetize the magnets significantly. And in this case, we can see from the graph on the bottom left corner that it goes from A and B as seen in the nonlinear demagnetization. So the knee point shifts significantly from the A position to the B position. And therefore, operating a permanent magnet machine at extreme temperatures will severely and permanently degrade permanent magnet machines. So now we look at the magnet state before and after the demagnetization. And for the demagnetization case, which was significantly affected by the demagnetization, at 5 milliseconds, we see that the magnets are not significantly demagnetized, just around the corners and the edges, which is expected. But at 20 milliseconds, there is a severe demagnetization. You can see it all across the magnets. And this results in the 27 reduction in the torque, and therefore the motor must be replaced at that point. So to conclude, we have to make sure that our traction motor operates within the expected range of power, and also maintaining the temperature at 120 degrees Celsius. So the NVH behavior of electric machines on electric vehicles is significantly different when compared with traditional cars. The lack of masking from combustion engine makes road and wind noise much more important. And auxiliary systems like the HVAC system, the power steering, and even the wiper motor are all of a sudden very audible. In addition to the powertrain must be quieter, but at the higher frequency noise tone originating from the electronics and the drive running the machine are extremely significant. And many places around the world are now placing standards to limit the noise emitted from those types of electric vehicles. And it's extremely important to take it into the design, not only just looking at the motor itself, but you have to be looking at the road noise, looking at the HVAC system, wind noise, electric motor, and the warning sounds around the vehicle. And of course, we progress to the final section of the presentation, where we discuss the cooling. And as we mentioned from the detailed demagnetization analysis, we have to maintain, for that given motor, we have to maintain the temperature in the windings at 120 degrees Celsius or even below. So what we're going to do here in this case, we're going to export the heat losses from the electromagnetic analysis and the demagnetization analysis. And of course, we've been using sim-center magnet. And then we're going to be mapping those heat the components, heat losses at sources, at heat sources for the different components in the design. And from there, we're going to optimize the cooling system. So let's see exactly how that looks like. We're going to start by having exactly the 3D model representation of the design, setting up the computation domain for the fluids, making sure that we have the components, and assigning the fluid subdomains. From there, of course, we're going to define the materials used in the design, setting the inlet and outlet of the cooling liquid that's going to cool the windings, and mapping the heat sources from the electromagnetic analysis to the components. And our goal, of course, is to minimize the temperature, to make sure that it falls under a given 120 degrees Celsius. So let's establish the baseline and look at the results without any cooling optimization. So just building the results, and let's see the definitions. So we're going to be looking into two results, the temperature and the pressure drop. So the temperature is already at 146 degrees Celsius, which is well above the level that we need, which is pushing us more towards the 27% reduction in the torque. So we have to optimize the cooling techniques. And what we're doing in this model, for example, here we're optimizing the pins in the cooling techniques and the pin count and the pin diameter, how they look and how many there are in the design to essentially to meet the objectives. So what we're going to do is we're going to set up the same optimizer that we use to generate the electromagnetic analysis and to study the 1,500 designs. The same optimizer, we're going to use it to minimize the temperature. So all you have to do now is just import the files from the simulation, the cooling simulation, allow the optimizer to auto tag the variables that we're changing, in this case, the pin count and the pin shape, and also assign the expected outputs, the temperature and the pressure drop. And as you can see, the optimizer automatically assigns and tags those inputs, and also the responses, which are the temperatures and the voltage drop, and the pressure drop, I'm sorry. And then we're setting the multi-objective trade-off, where we're considering 40 designs just to make it a little bit easier. Then we're setting up the objectives by simply dragging and dropping from the responses to the objectives. Is our objective to minimize the temperature and minimize the voltage, the pressure drop, and setting a restriction on the pressure drop, not to go below a given value, or not to exceed a given value. And all we have to do next is run the study. And once we run the study, the exact same interface, it just shows us as it progresses what's the infeasible designs, what are the error designs, and what are feasible designs. So at the end, we end up with 27 feasible designs and 13 infeasible designs violating one of the constraints. We're looking at the different data in the parallel plots, where we're viewing in the x-axis the different responses, and each line represents a design. And we're also looking at each of those designs. And now we're going to map those results back into the design and see the performance of the system, how it impacts the change. So doing the analysis and simulating the results and looking at the results, we can see now the temperature falls to 100 from the initial design to 119 degrees Celsius, which is well below the rated temperature, which amounts for 20% reduction in the shape, and this is the final cooling system. So with the intelligent design exploration techniques and the ability to couple the multi-physics together and looking at all those physics as one design process for the electric machine, we were able to design the electric machine, optimize the design, consider 1,500 designs, look at the required temperature, operating temperature from the demagnetization analysis, and then size the cooling system based on the demagnetization analysis. And as a result, we end up with the winding temperature at 119 degrees Celsius.